Every function you write hides decisions. Inside bisection root, one line decides how precise the answer will be for every person who ever calls it. That's a lot of power to keep for yourself. Python's default parameters hand that decision back to the caller without forcing anyone to make it. Start with code we've already written. Bisection root takes one parameter, x, the value whose square root we want to approximate. Inside, it sets up four variables. Epsilon are tolerance, a low endpoint and a high endpoint that bracket the answer, and a first guess, the halfway point between low and high. The while loop keeps going as long as the guess squared differs from x by at least epsilon. Each pass an if-else moves one endpoint. If the guess squared came in under x, low becomes the guess, otherwise high becomes the guess. Then we take a new halfway point between the updated endpoints. Every iteration cuts the bracket in half, so the guess closes in fast. One detail matters for everything that follows. When we wrapped this in a function, we return the guess instead of printing it. Printing shows a human a number. Returning hands the value back to the program, so the rest of your code can use it. And to call it, we wrote the function's name and one value, bisection root of 123. Here's the trouble. Epsilon lives inside the function fixed at 0.01. Every call from every user forever gets that same tolerance, but an engineer sizing a bridge might need 0.000001. Someone sketching a rough estimate will happily take 1 or 0.5, far coarser than 0.01. One hard-coded number cannot serve them all, and the person who knows what precision they need is the caller, not us. Option 1. Reach into the function and change the number. Set epsilon to 0.000001, and now everyone gets a very precise answer. The catch is that everyone gets it whether they want it or not. Every call site in every program that uses this function is affected by that one edit, and the people who only needed a rough answer now wait through extra iterations. Editing the body to serve one caller changes the answer for all of them. Option 2. Move epsilon out of the function entirely and let the user set it in the global scope. The function no longer defines epsilon, so when Python reaches that name, it pops up one level and uses whatever the user left there. This is worse. We've made our function depend on a variable somebody else owns. They might set epsilon once and forget to reset it. They might never set it at all, and the function dies on a name Python cannot find. Global variables are a poor idea generally. Here they hand control of our correctness to a stranger. Option 3 is the right instinct. Make epsilon a second parameter. The definition becomes bisection root of x and epsilon, and every caller must now supply epsilon as the second argument, so each one chooses their own tolerance. Notice what did not change, not one line of the algorithm. Epsilon was already a plain variable inside the function. The only difference is where its value comes from. Control has moved to exactly where the knowledge lives, the call site. Run it twice on the same value. Bisection root of 123 with an epsilon of 0.1 returns about 11.088. The same call with an epsilon of 0.000001 returns about 11.0905. For reference, the true square root of 123 is 11.0905365. The loose tolerance quits early, about 2 thousandths off. The tight one keeps halving and matches the true root through every digit it shows. Same function, same input. The caller picked the precision. But look at what we've done to the caller. Every single call now has to carry a tolerance, even when nobody cares. Worse, a new user has no way to know that 0.01 is a reasonable choice. Picking well requires knowing something about bisection search. You could write it into the function specification and then hope they read it. Relying on users reading documentation is a fragile plan. What we want is a middle path. The author supplies a sensible number and the caller overrides it only when they have a reason to. That middle pass is a keyword parameter, also called a default parameter. In the definition, write epsilon equals 0.01 right there in the parameter list. The function still takes two parameters. The difference is that the second one arrives with a value already attached, one we chose as the authors because we know what a sensible tolerance looks like. Two names for one idea. Keyword parameter, because you can refer to it by its keyword at the call, and a default parameter because it carries a default. Now the call side relaxes. Bisection root of 123 with nothing else runs without complaint even though the definition lists two parameters, because Python fills epsilon in from the default 0.01. And bisection root of 123 and 0.5 overrides that default. The value you pass wins and the function now stops once the guess squared is within 0.5 of 123 instead. Same definition, two behaviors, and the caller never had to learn a good default in order to get one. One rule governs the definition. Default parameters must come last. Write def bisection root x epsilon equals 0.01 and the Python is happy. Flip them, epsilon equals 0.01 first and then x, and the Python rejects the definition outright. It is not a style preference. The file will not run. The reason is mechanical. Python matches arguments to parameters left to right, so a parameter with no default can never sit behind one that has a default and might be skipped. That is the only rule for defining defaults. Once a parameter has a default, there are several ways to call the function, and the three of them are always fine. First, give values only for the parameters that have no default, bisection root of 123. Python supplies the rest from the defaults. Second, give a value for every parameter positionally in the order the definition lists them. Bisection root of 123 and 0.1. Nothing is ambiguous because Python pairs them one at a time, left to right. Third, name each parameter at the call. X equals 123, epsilon equals 0.1. The names come straight from the definition's parameter list. Because every value is labeled, you may list them in any order you like. Put epsilon first and x second, and the Python still assigns each one correctly. The third form is the one you can never get wrong. Two call forms cause trouble. The first mixes the styles in the wrong order. Epsilon equals 0.1, and then a bare 123. Python raises an error before running a single line because a positional argument cannot follow a keyword argument. Once you start labeling values, Python has lost track of which position it is up to, so an unlabeled value after a labeled one is meaningless. This failure is the safe kind. It is loud, it happens immediately, and you fix it before anything runs. The second is more dangerous. Bisection root of 0.001 and 123. Both values are positional, both sit in a legal place, so Python runs it happily. But read what it means. X becomes 0.001 and epsilon becomes 123. You have asked for the square root of 0.001 to within a tolerance of 123. That tolerance is so absurdly loose that the very first guess already passes the test. The loop body never runs even once, and the function returns a number nowhere near the true answer of about 0.0316. No error, no warning, just a wrong result. That is the failure worth fearing. Three things to carry away. Hard coding a constant inside a function decides for every caller, and hoisting it into a global hands your correctness to a stranger. A parameter with a default does neither. The author sets a sensible value, and the caller overrides it when they know better. In the definition, defaults always come last. And at the call, when you are unsure, name every parameter and its value. Python will never mismatch a labeled argument, and the reader of your code will never have to count positions. To practice what you just learned, this course has free exercises and AI graded feedback on ludium.ai. The link is in the description.